Hi, I'm NU from Purdue University. Today we present the paper High Resolution UAV Image Generation for Sorghum Panicle Detection. We would like to acknowledge Professor Ayman Habib for providing the images used in this paper and our project sponsor ARPA-E. The sorghum plant has been found to be a very good potential crop for biofuel. The biofuel from sorghum is less of a concern than the biofuel from the main food crops such as the corn, since the production of biofuel from those food crops could lead to supply shortage in food production. A sorghum panicle is a cluster of flowers at the top of the plants. The panicle, or the head of the sorghum, is one of the most important features of the plants that relate to the grain yield, plant growth, and management. Detecting and counting the panicles can provide the information such as the flowering date, so plant breeders can select the proper types of crops. In recent years, deep learning-based methods have been successfully used for the detection of objects from UAV images. Deep learning is highly dependent on the quality and the quantity of the available training data. A large amount of high-quality ground truth data are often needed to achieve the good performance. However, ground truth data like panicles on UAV images is very time-consuming and tedious due to the resolution and the density, which creating a major bottleneck for the applications. The data augmentation is a technique to increase the amount of data by adding slightly modified copies of existing data or create synthetic data from existing data. It can help reduce the overfitting issues during the training of machine learning model. There are multiple ways to do data augmentation, such as rotating, flipping, adding noise, or mask part of the image. If a dataset is very small, then the rotation and mirroring may not be enough for a given problem. In recent study, synthetic data augmentation shows improvements even for smaller datasets. Our proposed approach uses synthetic training images from GANs for data augmentation to enhance the performance of sorghum panicle detection and counting. Our methods consist of two parts: training a conditional GAN with a small amount of ground truth UAV RGB images of the sorghum, and then generating synthetic images with the random location of the panicles, which we use for data augmentation. In the first part, we use label maps and image pair for training the GAN. The label map is a grayscale mask acquired by converting existing ground truth bounding box labels. In the data augmentation step, we use random locations of the panicles as label map to generate synthetic images. In this way, the ground truth labels of synthetic image is predefined, so we can use it directly for the training. The synthetic images are then added to the real image dataset to form the training data. We require the GAN model to be capable of generating high-resolution images constrained by the inputs. So we choose two image-to-image translation GANs because the real image bounding box labels can be converted directly into masks. The Pix-to-Pix HD model has the multi-scale generators and discriminators that can help to generate high-resolution images. Due to the normalization layer inside the Pix-to-Pix HD model, it tends to lose semantic information during the training. And the SPADE model is an improvement of the Pix-to-Pix HD that used to preserve the semantic information by adding the SPADE blocks. We only have one class in our datasets with minimal semantic information, so the added blocks for preserving semantic information might not be beneficial. So we decided to use both methods and compare their performance. The real image datasets consist of a set of crop images from 4 orthomosaics of sorghum field. The image is acquired by a RGB camera mounted on UAVs flying at altitude of 20 meters. The resolution of the crop image is 1024 by 1024 pixels. Each of the crop image contains 4 row segments of sorghum plants in the vertical direction. The bounding box labels are converted into the ground truth label maps for training the GANs. In total, we have 500 manually labeled crop images as our experimental datasets. The results, the Panicle generated by Spade, are more realistic than those generated by the Pix2Pix HD. The Panicle edges from Spade are clear, while the Panicle edges of Pix2Pix HD are blurred. However, the Pix2Pix HD has a more natural background that resembles real sorghum images. The straight line on the right side of the synthetic images is learned from the real images created by the process of auto-rectifications. We generate 1,000 synthetic images for each of the GAN using random label maps. The random label maps are constrained in location and size of the bounding boxes such that the overall distribution is identical to real sorghum images in our datasets. In total, we have 1,400 images for training. We use YOLO v5 as our object detection network since it performs the best in the real image datasets during our test. Despite the different image styles generated by Pix2Pix HD and Spade, the data augmentation performance are similar. Both methods show improvements on Panicle detection and counting. The synthetic images of Pix2Pix HD have slightly better performance for the counting metrics due to the more realistic backgrounds. The future work will include developing multi-temporal methods that can generate synthetic plant images in a temporally consistent style. This will also allow us to estimate phenotypic traits as the plant grows.